Hi, before we get to the differential equation, what is an RLC circuit? An RLC circuit is a circuit consists of resistor, an inductor, and a capacitor, as shown in a diagram. RLC circuits are widely used in many electronic systems, most notably as tuners in AM/FM radios. The tuning knob varies the capacitance of the capacitor, which in turn tunes the radio. The capacitance of an RLC circuit can be modeled by second-order, constant coefficient differential order equation, and we'll get to that soon. But before that, let IT be current, QT be charge on capacitor, L be inductance, R be resistance, C be the capacitance, and ET be the electrical potential. According to Kirchhoff rule, the sum of voltage drops around any closed loop must equals to 0. In other words, EL plus ER plus EC equals to ET, where EL is the electrical potential over the inductor, ER is the electrical potential over the resistor, and EC is the electrical potential over the capacitor. Faraday's and Lenz's law states that the voltage drop across an inductor can be shown to be proportional to the instantaneous rate of change of current dL dt with constant L. Now, I know you're sick of rules and laws, but I promise this is the last one. Okay? According to Ohm's law, the voltage drop across a resistor is proportional to the current I passing through the resistor with R as a constant. Last but not least, the voltage drop across a capacitor is proportional to the charge Q on the capacitor with proportionality constant 1/C. I know you've been waiting for this, so this is where the differential equation came into play. By substituting the aforementioned terms in the Kirchhoff rule equation, we get L dI over dt plus Ri plus 1/CQ equals to ET. And since I equals to dQ over dt, the final equation would be L d to the power of 2q over dt to the power of 2 plus R dq over dt plus 1/CQ equals to ET, which is in the second order of differential equation. As simple as that.
As for example 1, find the charge on the capacitor in an RLC series circuit where the inductance equals to 5/3 Henry, resistance equals to 10 ohm, capacitance equals to 1/30 farad, and the electrical potential is 300 volt. Assume the initial charge on the capacitor is 0 coulomb and the initial current is 9 ampere. What happens to the charge on the capacitor over time? First, we need to apply the second order differential equation. L d square q over dt square plus R dq over dt plus 1/C q equals to ET. Given that the value of inductance is 5/3 Henry, the value of resistance is 10 ohm, the value of capacitance is 1/30, the value of electrical potential is 300 volt. Substitute the values given and we'll get the equation of d square q over dt square plus 6 dq over dt plus 18q equals to 180. After that, we must find the solution for the homogeneous equation. First, we must substitute dq over dt as m. Then the solution will become m squared plus 6m plus 18 equals to 0. After that, we use the formula negative b plus minus square root b squared minus 4ac over 2a. Then we will be able to find the roots of this equation. After that, we will be able to find the solution for the homogeneous equation, as shown in this slide. Then, to solve the particular part of the equation QPT, you need to take note of the right hand side of the equation to get the function ft equals to 180. The formula of QPT is t power r c0. First, we substitute the value of r equals to 0 into QPT. We'll get QPT equals to c0. The coefficient of QPT is similar with ft. Then, we do not need to substitute the continuous value of r into QPT. To get the equation of q prime pt, we'll need to differentiate qpt, then we'll get q prime pt equals to 0. After that, to get the equation of q double prime pt, we'll need to differentiate again q prime pt, then we'll get q double prime pt equals to 0. From the differential equation, we'll see that q double prime plus 6q prime plus 18q equals to 180. We need to substitute the value of q double prime, q prime, and q into the equation. We'll get 0 plus 0 plus 18 c naught equals to 180. Lastly, we'll get the value of c naught. The general solution of qt is the homogeneous part plus the particular part. Then we'll get e power negative 3t times a cos 3t plus b sin 3t plus 10. The conditions given in the questions is when t equals to 0, q equals to 0. When t equals to 0, I equals to 9 ampere. The equation of current, which is I, is the differential equation of qt. When t equals to 0, q equals to 0. Therefore, we substitute the value of q and t into the general solution, we'll be able to get the value of a, which is negative 10. On the other hand, to get the equation of current I, we need to differentiate the equation of charge qt. We'll differentiate and get the equation of 3b minus 3a times e power negative t cos 3t plus negative 3a minus 3b times e power negative t sin 3t. Given that the value of I is 9 when t equals to 0, we can get that 9 equals to 3b minus 3a. After that, substituting the value of a, which is negative 10, into the equation we have just now, we'll be able to solve the value of b, which is negative 7. After that, we substitute the value of a and b into the equation of qt, then we'll be able to get the particular solution of qt, which is negative 10 e power negative 3t cos 3t minus 7 e power negative 3t sin 3t plus 10. Lastly, we'll find the charge on capacitor over time. We'll limit the value of t in qt approach to infinity so that we can get negative exponential in the equation. And then we will be able to get a steady state charge of 10 coulomb. It is because the negative exponential will eventually give us a value of 0. And that's all for example 1. Thank you.
Now for the example 2, the question is find the charge on capacitor RC series circuit with given the RC and E with the initial value. From the differential equation, substitute all the value into the differential equation and rearrange to be the second derivative q plus 2 multiply the first derivative q plus 10 multiply q equal 250. Then using characteristic equation to find the value of m. The value of m is minus 1 plus or minus 3i. So we get QH of t equation. Now proceed to particular integral QB of t. We know that f of t equal 250 and QB of t equal t power r multiply c. Now let r equal 0 and QB of t equal c, which has no similar coefficient compared to QH of t. So we differentiate QH of t and we get that QB of t equals c and the first and second derivative QB of t equals 0. Then substitute c into differential equation to calculate the value of c, which is 25. So we get the particular integral solution QB of t, which is also equal 25. In order to get the general solution, we sum up QH of t and QB of t. Next, apply the initial value given when the time is 0 and charge is 0 and current is 4 ampere. Substitute 0 into Q of t. We get that A equals 25. Meanwhile, to get the current equation, we need to differentiate Q of t. Then substitute I multiply 0 equal 5 and solve for B. Then as a result we will get the particular solution of Q of t.